All right. Good morning, guys. Sorry if I sound a little tired. I'm doing this pretty late at night. But today, as promised, we're going to spend a little bit of time reviewing concepts from grade 11. And there's two main things I want to cover today. One is significant digits and what we mean by that. And then the second is just doing a little bit of dimensional analysis to make sure that we can all go from moles to mass or from mass to moles. So we'll go through this quickly. The first one is significant digits. And if you've done this before, great. If not, it's brand new to you. There's nothing wrong with that. The basic idea is this. Anytime we measure anything in science, we use some kind of device to do it. We have to use an instrument. So for example, let's look at these measurements here. They're all measured with some kind of instrument, which means they're all approximations. They're all measured to the nearest something. I'll show you what I mean. 23 milliliters is measured to the nearest milliliter. And that actually means that this number could be anywhere between 22.5, well, 22.6 we'll say, because that would round to 23, all the way to 23.4. Anything in that range would round to 23. So if we say something is 23 milliliters, it doesn't mean that it's 23 milliliters exactly. It just means that whatever device we're using to measure it gave us 23, which means that it's a number that would have rounded to 23. Likewise, 13.4 is now measured to the nearest 0.1 milliliters. That's 10 times more precise, but it still isn't exact. What it means is this. That could be as small as 13.36, because rounding rules, or even 5 actually in this case, because a perfect 5 rounds to the even number, which isn't important. 13.35 would round to 13.4. It's the lowest number that would. And 13.44 would round to 13.4. It's the highest number that would. So this number here actually represents a range. You try the next two, make sure you understand it, and then we'll take them up. So you can pause the video. We'll assume that you've paused it, and now you've unpaused it. So 123 meters is measured to the nearest meter. And that means that the lowest number that could possibly give us that would be 122.6. And the highest number it could possibly be would be 123.4, because that would round down. And again, this number isn't exact. It represents a range. It's an approximation. Now, what do we do with 100 grams? And this is where significant digits comes in. We have no idea what this is. It could be to the nearest gram. It could be to the nearest 10 grams. Or it could be to the nearest 100 grams. We just don't know. The number is ambiguous. If it's to the nearest gram, then this would be somewhere between 99.5 and 100.4. But maybe when they say 100 grams, they measure it to the nearest 10, in which case this is somewhere between 95 and 104. And for all we know, it's actually measured to the nearest 100 grams, in which case this could actually represent a number as low as 51, because that rounds to 100, and as high as 149, because that rounds down to 100, measured to the nearest 100 grams. And this is important because it is ambiguous. It's unclear what's actually meant by this number. And this leads us to a rule that we call significant digits, which just means measuring which numbers or which digits in a number are actually giving us useful information. So I'm going to give you some rules here, or I'm going to share some information here, and I'm actually going to have you try and remember the rules yourself. I will say that 132 grams has 3 significant digits. 100 grams has 1. 100.0 grams has 4. 0.003 grams only has 1. But 1.003 has 4 grams. 0.000300 has 3, and 103.040 has 6. So take that for a minute, pause, talk to your friends, and see if you can work out the rules. Pause this video, and we'll fill them in together after. Well, you're back, and let's see what we can learn from this. The first rule I would say is that one thing we can always be sure of is any non-zero number is significant. And when we say significant, what it means is this: that number has been measured and it's meaningful. You actually had to look at a piece of equipment to get each of those digits. The 1 is the number in the hundreds column, the 3 is the number in the tens column, the 2 is the number in the ones column, and they all had to be measured off of some kind of device. So those are all significant. And you never have to worry. If a number isn't 0, it is significant. But now let's look at what this rule tells us. Actually, let's look at, yeah, no, that one's good. Because this can give us our second rule. Any zeros on the far right are not significant. And the reason being, we can't be sure if they were measured or not. It's unclear. That 100 could have been measured to the nearest gram, but it could have been measured to the nearest 10 grams, and it could have been measured to the nearest 100. We're not sure. So all we know for sure is that that 1 had to be measured, and those 2 zeros aren't clear, unless we're told otherwise. So unless someone specifically says, oh, we measured this to the nearest 1 or to the nearest 10, any 0 to the right we assume is just a placeholder. We assume that it's to the nearest measured number, nearest non-zero. The only exception to that is zeros after a decimal place. So zeros on the end of a number after a decimal place are significant. The reason being, if you look at a number like this, they didn't have to put that 0 in there. 100 and 100.0 are mathematically the same number. So the fact that they put it in there means that they had to make a point of doing it. So it matters. Next, zeros before a non-zero are not significant. They're just placeholders. And those 4 rules actually get you everywhere. These middle numbers here, any middle numbers always are significant. So it's only the ones on the end that you have to worry about, that you have to think about. Any numbers in the middle, even if they're zeros, they count. And that's why this is 4, this is 6. It's only here where, for example, these ones don't count, but the ones that do. So we're going to do a bunch of practice just to make sure you've got it. So let's use this space. Let's do some examples. So I'll give you a few first. Let's say 136.02. Let's say 0.0417, 0.0408, 123.0, 120. All right, try those. take a minute and work them out. All right, and we're back. Here, the only 0 is in the middle, and zeros in the middle always count. They had to be measured. Before I could measure how many hundredths we have, I must have measured the tenths. So these are all significant. So 1, 2, 3, 4, 5 significant digits. This next one, the 4, the 1, and the 7 are all measured, but these 2 zeros out in front are just placeholders. Numbers in front are always just placeholders. Any number that comes before a non-zero doesn't count. So the 4, the 1, and the 7 are measured, meaning this has 3 sig figs. This next one, again, the 2 numbers in front don't matter, but this 0 we like because numbers in the middle are measured. I have to measure that 0 before I could measure that 8. So these 3 all count. That's 3 sig figs. This 123.0, the 0.0 on the end, is completely unnecessary. So the fact that somebody took the time to write it tells me it must be significant, because otherwise you just wouldn't write it. So that's 4. And 120, this one here is unclear, so we're not going to count it. We say this has 2. Hopefully you did well on that. Let's try just one more set of them, just to make sure we're all on the same page. Let's say 0.0300. 118.52, 97.103, and 104. So take a minute, do those, and then we'll come back. All right, in this case, the numbers in front are just placeholders. These numbers at the end are unnecessary because we're after a decimal place. Decimal 03 and decimal 0300 are the exact same number. So the fact that somebody bothered to write those tells me they count. 3 sig figs. Every number in this is a non-zero, 1, 1, 8, 5, 2. They all matter, so there's 5. 97.103. Any 0 in the middle of a number is significant, so 1, 2, 3, 4, 5. And again, 104. Any 0 in the middle of a number is significant, so all 3 of those count. All right, and then the rules, if we remember, are actually pretty easy. For multiplication and division, the rule is as simple as this. Count significant digits for each number involved, and the answer should be the same as the lowest number of sig figs. So the reason we have to do this is we have to be careful not to make our answer more accurate than the numbers we work with. So for example, let's do 12.27 times 1.82. Do that on your calculator and see what answer you get. I get 22.3314. The thing is, these numbers, whatever device I measured this on, give me how many significant digits? 4. And this device had 3 significant digits. So if I had 4 significant digits from the first device, maybe it was a scale, and 3 significant digits from the second device, maybe it was a pipette that we used to measure volume, something like that. How can I possibly get 1, 2, 3, 4, 5, 6 significant digits in the answer? And the answer is I can't. You can't have a more precise answer than the numbers you started with. So we have to round this to 3 sig figs, because that's the lowest number in the question. And so we're going to round to this number. There's a 3 next to it, so this would be 22.3. I'm done. Let's try one more example. And we'll do two more. We'll say 1.245 times 3.8. And we'll also do 3.12 times 5. So take a minute and work those out. All right, this first one, when I do it on my calculator, I get 4.731. But again, if I look at my question, yeah, 1.245 has 4 significant digits, but 3.8 only has 2. And again, my answer can't be more precise than the numbers I used to come up with that answer. My answer can't be more precise than the numbers I used to get there, which means I can't end up with 1, 2, 3, 4 sig figs in my answer if I only had 2 to begin with. So I've got to round this to 2 sig figs, which means these 2 digits have got to go. That 3 means we're going to round down, not up. So this would be 4.7 as an answer. Good. And again, we can try this over here. This I should be able to do in my head, you would think. It should be 15.6, I think, but let me just try it. Yeah, 15.6. And this is one we got to watch out for. Classic mistake. Yeah, it's 3.12, which is 3 sig figs. But when we say multiplying by 5, keep in mind, don't forget, this is only 1 sig fig, which means this could be anywhere between 4.6 all the way up to 5.4. We don't know what that number is. And so the rule is, if we only have 1 sig fig here, we've got to round this to 1 sig fig. And that means that these 2 numbers are going to go. And here we have a 5, 6. This is bigger than halfway. So this is going to round up to the 2. And it's not 0.5 exactly. Or this 5 that we're rounding isn't half exactly. So this is going to round up no matter what. So 20. And remember, this is only 1 sig fig, because that 0 is ambiguous. All right, talk to your peers around you. Make sure that makes sense. And now when we're done that, I just want to mention this note, that whole numbers have an unlimited number of significance, as in counting numbers. And what I mean by that is this. If one hairdryer uses 1.2 kilowatts of power, then 2 of them use 2.4 kilowatts. This 2 would have an infinite number of sig figs, because there's no such rounding. If I say there are 8 people in the room, I mean 8 exactly. I don't mean those 7.5, and I don't mean those 8.5. I don't mean those 8.2, and I don't mean those 7.8. No matter how much Caleb is going to try to convince you over the next 5 minutes that I only count as 0.8 of a person, it's just not true. When we count things, that's different. Counting is infinitely significant. So any number we count has unlimited sig figs, and you don't consider it when doing your multiplication. All right, now when we add and subtract, multiplication is easy. We count the lowest number of sig figs. Adding and subtracting is a little bit different. We don't count sig figs. Here we count decimal places. You can review your grade 11 notes if you want to know why, but we don't count sig figs, we count decimal places. So 5.667 has 2, 1.1 has 1, 0.9378 has 4, 7.7 has 1, and I didn't say, but 8 has none, right? And 210, not only does it not have a decimal place, but it doesn't even have a 1. Anyway, we'll look at some examples like that. So let's look here. Let's do a few examples. 18 plus 132 0.2. Let's do 7.41 plus 9. And lastly, let's say I'm 34 now. How old will I be in 50 years? All right, so try these out. Pause for a minute, talk to your peers, and we'll try them out. All right, here. Well, if we do this in our calculator, we would get 18 plus 132.2, and we would get 150.2. But don't forget, this has no decimal places, and this has 1 decimal place. Well, we have to go with the least. So we have to make sure our answer has no decimal places, which means that 0.2 gets eliminated, and this would just be 150. In this next case, if I plug this into my calculator, it's going to say the answer is 16.41. But again, here we have 2 decimal places, but the answer has no decimal places. So the answer must have no decimal places. This again rounds down. 41 is less than half, right? 0.41 is less than halfway. So this rounds down to 16. In the last example I gave you here, 34 has no decimal places, but it's the nearest 1. 50 has no decimal places, and that 1's ambiguous. That 0, we don't know if it's measured or not. So this is actually to the nearest 10. And we have to go with the least precise. Nearest 10 is less precise than the nearest 1. Whoa, that was crazy. So when we add this on our calculator, it's going to tell us 84. But we know that since we didn't measure the 1's column in 50, this 1's column can't be meaningful, because this could have been as low as 46, or 45 even, and could have been as high as 54. So we can't trust that 1's column in the answer, and this would just be 80. So there you have the rules for significant digits. If you guys are feeling exhausted from this, you can pause this now and just work on some practice there. I've given you some ideas and some rules here. If you're feeling brave and like you want to keep going on the next bit, you can do so. If not, you can try it on your own time. Load this video up. If you want to focus on the sig fig stuff right now, totally get that. Nothing wrong with it. If you feel like, no, we all get that, that was easy, then you can go on and remind yourself about moles and masses. And all I want to do here is just remind ourselves that if we know how many moles of something we have, we can figure out what that weighs. Or if we know the weight of something, we can figure out how many moles we must have. And the reason, remember, is that 1 mole of something equals its atomic weight in grams. So let's get going. Let's look at sodium hydroxide. So the first thing we have to do here with sodium hydroxide is work it out. We have sodium, which is Na. If you look at the periodic table, what charge does sodium take? +1. The hydroxide ion, you'd have to look up in a table if you don't remember it, but it's OH and it takes a charge of -1. Now for these two things to form a compound together, Na +1, OH -1, they balance out at NaOH. And now, if we wanted to know how much a mole of this weighs, actually, you know what, guys? You know what? scrap this. I'm going to delete this from this part of the video. We're just going to do some practice from before. So we will do this due on Wednesday. Yeah, we're going to do that on Wednesday. Okay. So work on your significant digit stuff, and we'll be good from there. Ciao.